All right. Can you all see the screen? Or I think I have not shared yet. Okay, sorry. Okay. So good morning, everyone. Are there any questions or concerns regarding anything we discussed last time? Right. So we were in the process of proving this theorem, which is giving an algebraic characterization of extreme points. Right. So the way we define an extreme point is that it's a point that cannot be expressed as a convex combination of two other points, two distinct points. And now we are proving that this definition is the same as saying that the rank of the matrix formed by the tight constraints for this point x bar, it's a full rank matrix. So its rank is equal to n. Right? So, all right. So I wanted to correct, I think towards the end I was rushing a bit and I made a couple of mistakes in the proof. So I just want to correct that. So we got to this point where we notice that what's here on the left side is the same as what's here on the right hand side. And that means that everything should hold with equality. In particular, we should have an equality here. And now if you think about it, why would you have equality? Well, you would have equality if this quantity is equal to this quantity. And likewise, this quantity is equal to this quantity, right? Because if either of them is a strict inequality, then you will have a strict inequality everywhere, and that would be a contradiction. Right? So these two should be the same, and these two should be the same. And at that point, I think I jumped to a conclusion which was not right. So what you can conclude from here is that either lambda is going to be 0 or 1, in which case, because you have a full rank matrix, either x bar will be the same as x prime or x bar will be the same as x double prime. Okay, so that's because there is a unique solution. And if lambda is not 0 or 1, then it has to be in the open interval 0, 1, in which case, again, because of unique solution, you will conclude this time that x bar, x prime, and x double prime are all the same, right? But in either of these cases, you can conclude that x bar is not a proper convex combination of two distinct points in your polyhedron. Okay, and that is the same as saying that it is an extreme point, because you cannot write it as a proper convex combination of two distinct points. Okay, so apologies for that confusion. I took a slightly different approach from the proof in the text, and that is why I had to make some other changes. Are there any questions, concerns regarding this? So this red colored part is what I have modified because there was an error in the last lecture. All right, so we have proved one direction. We started by saying that the rank is n, and we proved that it is an extreme point, right? Now we want to prove the converse. So we are going to do it by the contrapositive. We are going to assume that the rank is less than n and show that it cannot be an extreme point. Okay. All right, so let's start with that. If the rank of the matrix corresponding to the tight constraints at the point x bar is strictly less than n, then x bar is not an extreme. Okay, let me give you the geometric intuition before we write down the rigorous details. So let's see, let's draw our usual polytope, polyhedron. Okay, and let's suppose we are looking at just three constraints.
I think you're on mute.
Okay. Am I audible now?
Yes.
Okay. So what was the last thing you heard?
Just the beginning of, right after you draw the figure, it's
Okay, okay, got it. All right. So let's say this is our example in R2. Okay. And we are looking at some point x bar, and the rank of the tight constraints is not 2, it's less than 2, right? Which means your point can belong to any one of the lines I've drawn, but it cannot belong to the two lines. It cannot be the intersection of two lines. Okay. So, which means that your point won't be one of the 3 points that I have marked here. And what we want to do is we want to write down this point as a convex combination of 2 points. So we need to find out an x prime and x double prime, so that x bar is going to be a proper convex combination of these 2 points. Okay. So we want to use this information to somehow come up with x prime and x double prime. So the plan is, so let's suppose that the rank of the matrix corresponding to the tight constraints is less than n. Okay. And our plan is to construct x prime and x double prime such that we will write it to be half times x prime plus half times x double prime. So these should be distinct in our polytope. Okay. All right. So how do we do this? Anyone has any ideas? What does it mean for the rank to be less than n? Using this information, what can we infer?
That a vector can be expressed as multiple linear combinations.
Or specifically that if there is a solution and there are infinitely many solutions.
Okay. Can you say something about the columns of this matrix?
They are linearly dependent.
Right, exactly. Which means that I can take a linear combination of the columns to get the zero vector. Right. So it's equivalent to some of the things others said. Right. So some linear combination of the columns produces the zero vector, some non-trivial linear combination. Of course, you can take the all zero combination, but that's not what we are saying, right? In particular, it means that there exists some vector D which is non-zero such that I get the zero vector. Right? Okay. So we are going to use this vector D to get our x prime and x double prime. Okay. So in particular, our plan is to write down x prime as x bar plus epsilon times D and x double prime as x bar minus epsilon times D. Right? Note that if we do this, we get that x bar is exactly half times x prime plus half times x double prime, as we intended in the earlier plan. Right? And in particular, if epsilon is greater than 0, then we also get that x prime and x double prime are distinct. Right? We wanted them to be distinct. So we just need to show that there is some epsilon greater than 0 so that both of these points are going to be in our polytope, in our polyhedron. Right? So it remains to show that we can choose a small enough epsilon such that both of these points will belong to our polyhedron. I think I called it P, right? Let me make sure I'm using the same notation. Yeah, that's our polyhedron, right? Okay. So what does that mean? It means that we need to show that x prime in particular satisfies the constraints of our polyhedron. Let us recall that our polyhedron is defined using these linear inequalities. Okay, so that means that we can think of these inequalities as the tight ones and the non-tight ones separately. Okay, so what we are calling the slack constraints. So let's first consider the tight constraints. Okay, so let's look at the tight constraints for x bar and let's see if those are satisfied by the point x prime. Okay, so well, what is this? X prime has been defined as x bar plus epsilon times D. So right, and that is exactly this plus epsilon times the tight constraints multiplied by D. Now, because these are the tight constraints, by definition, this is exactly equal to the right hand side corresponding to the tight constraints. And since we chose D using the linear dependence property, right, we have that this is exactly epsilon times the zero vector. Right? And that's exactly So geometrically what we are doing is for the tight constraints, we are basically moving along the same hyperplane, right? So the new points we get, they are still going to belong to those hyperplanes for which the constraint is tight. And now we need to look at the non-tight constraints and see what's going on there. Are there any questions or concerns at this point? Right. So the conclusion at this point is that x prime and similarly x double prime, the same argument goes through, satisfy all of the tight constraints corresponding to x bar. Okay. So now let's consider one of the slack constraints. So let A transpose x less than equal to beta be one of the constraints that has not been covered in our tight ones. Right? Denote one of the slack constraints at x bar. Okay. So now let's evaluate this constraint at x prime. So that is, instead of x prime, I'm going to write down x bar plus epsilon times d. Is that right? Yeah, it was a plus one. And this is A transpose x bar plus epsilon times A transpose d. Okay. This we know is not a tight constraint because it's a slack constraint. So this is strictly less than beta, right? This is strictly less than beta. And we want the whole thing, we need this to be less than equal to beta, right? But that we can always do, right? Because if this quantity is less than beta, so we have some gap and we can always make epsilon small enough so that this quantity will be less than equal to beta. Does everybody agree? I can keep making epsilon arbitrarily small, but never making it equal to 0, and I can satisfy this constraint. Does everybody agree? So if I look at all the slack constraints, I can choose an epsilon that will satisfy all of the slack constraints, because each time you will have a strict inequality in this case. So we may choose epsilon to be small enough but not 0, to satisfy such that x prime and x double prime both satisfy all of the slack constraints. Right? And that's it. That means, in particular, we have shown that x bar is a proper convex combination of distinct x prime and x double prime in our polyhedron, and in particular, x bar is not an extreme point. Are there any questions or concerns? Was there any part that wasn't clear? right? The key point is that we have strict inequality, so we can make epsilon small enough and satisfy the inequalities we want. And if we choose a minimum epsilon for all the constraints, all the slack constraints, then that minimum will work for all of them simultaneously. All right. Good. Okay, so that completes the proof of this theorem, right? And so now we have two different ways of thinking about extreme points. The geometric way of thinking about it, which is the definition, and this more algebraic way of thinking. All right, so okay, so I want to move to one more topic in convexity, which some of you may have seen in other courses in probably a different context. I want to talk about the convex hulls. Let's look at some examples in R2. Can anyone tell me what is the convex hull of these 3 points?
The triangle.
Triangle formed.
Triangle, exactly. The triangle formed by these 3 points. The unique triangle whose 3 corners are precisely these 3 points. Okay. How about 2 points?
Line segment.
The line segment joining these 2 points. Okay. How about I put 4 points in this kind of position?
Join all the points.
Okay, so it's a unique convex quadrilateral containing all of these points. And the last one, what about these 3 points?
It will be the triangle only.
It will still be the triangle corresponding to these 3, and the 4th one will line the interior. Right? So the convex hull is not just the boundary, but also includes all of the interior. Okay. So what exactly is the convex hull? I mean, you all can tell me what it is on examples. How would you define it?
Like any point inside the convex hull, you can write as a linear convex combination.
Okay, so is it the set of all convex combinations?
Yeah, a set of all convex.
Right. Okay, so that is one definition. Any other way to define it? We will probably have a short discussion on why these definitions are equivalent. So one definition is indeed, it is a set of all convex combinations of your given finite set. Given a finite set S in Rn, the convex hull of the set S, which we will denote like this, right, is, so one of the definitions, I'm going to put it as number 3, it's a set of all convex combinations. And we will have to actually talk about convex combinations in this context. Of S. But when I say of S, I mean of points in S. Any other ways to define it? Okay.
The area enclosed by a rubber band that starts off enclosing all of the region and then contract it to cover just these points.
Right. So I think that works in 2 dimensions. So that is a very good intuition for 2 dimensions. Does it work in 3 dimensions as well? Well, in 3 dimensions, how do we really
There we have an elastic sheet that is wrapped around.
Right, right. So those are very intuitive ways of thinking about it in 2 and 3 dimensions. I'm not going to write that down. So they are indeed valid ways of thinking about it, and perhaps more intuitive than the formal definitions we are going to be looking at. The only trouble is that when we go to higher dimensions, we don't know how to generalize. But yeah, those are indeed correct ways of thinking. Let me ask you the following. If I take any convex set containing all the points given to me, will it contain the convex hull? Right, supposing I'm given a bunch of points S. So this is like now what I'm drawing is a Venn diagram. So don't think of this as a 2D space anymore. So if I'm given a bunch of points and I look at any convex set containing all of these points. So let's say this is some convex set. That contains the given set of points S as a subset. Right? So this should contain all of the convex combinations anyways, right? So in particular, any such set should be a superset of the convex hull. And if I take another set, which is also convex and contains this, that should also be a superset of this set. So let's say Ki is some convex set containing S. There could be many more such sets. And what the convex hull is, it's the intersection of all such possible sets. So that is another way to think about the convex hull. So it is the intersection of all convex sets containing the given set S. And from this point, you can actually see that this is the unique minimal set that is convex and contains S. So it is the unique minimal convex set that contains S. So these are at least 3 different ways of defining the convex hull, and the fact that they are all equivalent is not that difficult.
So like, what do you mean by minimal?
Right. So minimal is similar to the use of maximal on your assignment. So basically, any other convex set that contains S. Okay, so minimal means that if you take any proper subset of this set, it will not satisfy the property you want. So it won't be a convex set containing S. Right? So minimal means you keep removing things until you can, but your property has to be satisfied. What is the property? It should be a convex set that contains your set S. With respect to this property, it is minimal. Does that make sense?
Yes.
So it is very similar to the way I have used maximal on your assignment problems. So typically when you say minimal or maximal, it's not clear whether it should be unique. But in this particular case, it happens to be unique. And the way to see that is that this definition number 1 is the same as definition number 2. And the second one, it's clearly unique because you take all possible convex sets in the world containing the set S, their intersection is going to be well defined. So it has to be unique. You can't have two different possible intersections of a bunch of sets. Right? It's unique if you define it as the intersection of a bunch of sets. Right? So I think I would like you to all try these equivalences yourself. So show that these definitions are equivalent. Okay, and the way you want to go about it is you first show that 1 and 2 are equivalent, and then you show that 2 and 3 are equivalent. So that is one approach. There is one point that we have kind of not discussed. What exactly do we mean by convex combinations? In our previous discussions, when we defined convex combinations, we only talked about 2 points. We said it's lambda x prime plus 1 minus lambda x double prime. However, there is a more general definition which is actually used here. It's basically like a linear combination, except that all your coefficients have to be non-negative and they should add up to exactly 1. Okay, so given a set S in Rn, any vector x bar let's say S is let's say it's x1, so these are superscripts. These are, let's say, up to xk. So given any k points in Rn, if I am able to write x bar as lambda 1 times x1 plus lambda 2 times x2, where all of the lambdas are non-negative and the sum of all the lambda i's is exactly equal to 1. This is said to be a convex combination of these points. Okay. So why are we going to this more general definition? Well, here is the intuitive idea. So if you take the convex combinations of the first 2 points, you will get precisely this line segment. You take the convex combination of the second 2 points, you get this one. And the third, you get this one. However, now you can think about it this way. If you take any convex combination, if you want to write any point here, you can write it as a convex combination in this sense for all 3. First, you would draw a line segment like this, and this point can be written as a convex combination of the first 2 points. And now you can, let's say I call this x star. And now you can take x star and x3 and write x bar as a convex combination of those 2. And if you expand out, you will see that it basically means that this point is a convex combination of all these 3 points for some lambda 1, lambda 2, lambda 3, which will satisfy this definition. Okay, so by taking all possible convex combinations, you will actually get the entire area inside your triangle in this example. Okay. So when we are saying convex combination here, we are referring to this more general definition that is applicable to any finite number of points rather than just 2 points like we were discussing earlier. Okay. Good. All right. So why do we care about convex hulls? Let's go to one of our examples. Maybe the example that I drew earlier. So no, this one is a polyhedron. I want to go to a polytope. Let's look at okay, it doesn't matter. I'll just redraw it. Right. So if you look at our LP1, I'm just going to write down the constraints. Right. So we have the following constraints. 2x1 plus x2 less than equal to 9, x1 plus x2 less than equal to 7, minus x1 plus x2 less than equal to 5, x1 is at least 0, and x2 is at least 0. And how do we plot this? So we have the point 1, 2, 3, 4, 5, 6, 7, 8, 9. And we had 4.50 over here. And this was one of our constraints. And then we had this one and this one. And then we had this one here and this one here. And our polytope that we got, the feasible region, is exactly this. Okay. And notice that this polytope P, it's nothing but the convex hull of the extreme points. Observe that the feasible region P of LP1 is simply the convex hull of its extreme points. And this is in fact true for any polytope. For any polytope, it can be thought of simply as the convex hull of all the extreme points of that polytope. So I'm just going to state it as an observation because I'm not sure if you'll be proving this formally in this course. It might be a bit going too much beyond the scope of the course. So any polytope in Rn, or if we do prove it, it will be after duality. So that would be module 4, after module 4. Any polytope in Rn is the convex hull of the extreme points of the same polytope. Okay, so I hope intuitively kind of makes sense, at least in 2D and 3D you sort of see this. Turns out this is true in general, but if we want to prove it rigorously, we might need some of the theory that we are going to develop in the next 1 or 2 modules. So whether we prove it rigorously, we will see later. But the reason I want to talk about it is because I want to give you some intuition about the geometry behind some of the combinatorial problems that we have written earlier, in particular for the perfect matchings. Okay, so are there any questions or concerns regarding convex hulls? Right, so whenever the feasible region of your linear program is a polytope, you can think of it as the convex hull of its extreme point. So that gives you another way to think about what the feasible region of a linear program looks like in the cases when it is a bounded feasible region, right? So that would be a polytope. Okay. All right. So I would like to talk about a particular polytope, which is called the perfect matching polytope. And this is going to be particularly relevant to us when we talk about finding a minimum cost perfect matching. So that's why I just want to discuss this a little bit before moving on to the next module. Okay, so let's say you're given some graph G. And I'll take an example to illustrate everything. So can anyone tell me if this graph is a perfect matching or not? And if there is, can you give me one, please?
We can have the top edge, middle edge, and the bottom edge.
Right, exactly. So these three edges, that is one perfect match. Okay. So what we are going to do is we can think of perfect matchings as we have done before as vectors, right? We can think of this being a 0, 1 vector where we have one component, one entry in the vector for each edge of the graph, right? So I'll put a 1 on these three edges and I'll put a 0 on all the other 6 edges. The main point is that each perfect matching may be thought or may be viewed as a 0, 1 vector in RE. Right? So in this case, we have 9 edges. So we are looking at Rn. Okay, great. So can we count the number of perfect matchings in this graph? Can anyone help me in counting the number of perfect matchings? So this is one perfect matching, the red colored perfect matching. I'll give you a hint. What can you say about these three edges with respect to any perfect matching? So these three edges can be thought of as a cut, right? This can be, the left side can be your set Z and the right side can be your set Z bar. So for any perfect matching, what can you say about M intersection partial Z? What can the intersection of your perfect matching be with these three edges?
Greater than 1. Greater than equal to 1.
Greater than 1, great. It sorry, greater than equal to, you mean, right?
Yeah.
Okay, it is greater than equal to 1. Can it be 2?
Oh, it should be
Notice
odd.
it can't be 2, right? Because there is an odd number of vertices in Z and there is an odd number of vertices in Z bar. So an odd number of them have to be matched into Z bar, right? So which means you have to either use one edge from these 3 edges, or you have to use all the 3 edges, which we are already looking at the red colored perfect matching. So in particular, it's either going to be 1 or 3. And if you choose only one edge, for example, if you choose the top edge, then you can't choose these two because we are choosing only one edge, and then you have to choose these two. And you can observe that this is symmetric. Well, one way to think of the symmetry is to redraw the graph like this. If you redraw your graph like this, you can see the symmetries more easily. It's just a rotation. So how many perfect matchings do we have now? Does anybody see how to count that?
4.
4, exactly. Either you take all 3 edges or you take one of the 3 edges, and if you take one of the 3, then the rest is determined. So you get a total of 4 perfect matches. Okay, so that means that in this case you get 4 0 1 vectors in RE in R9. So we have 4 perfect matchings which can be viewed as 4 0 1 vectors in R9. And now what we can do is we can take the convex hull of these vectors. And that object, that geometric object, is called the perfect matching polytope of your graph. So, given any graph G, the perfect matching polytope, PMP, is the convex hull of script M, or right, let's say script M of G, where script M of G is the set of all perfect matchings of your graph, and I'm going to put in brackets, viewed as 0 1 vectors in the right dimensions. Okay, so I'm looking at all these 0 1 vectors and I'm taking the convex hull of these vectors, and that's going to be the perfect matching polytope of the given graph. In this particular example, you are looking at R9, but you have only 4 vectors. So these 4 vectors, they are going to look like a tetrahedron in R9. Okay.
Like, is there something interesting about this?
Right. We are going to talk about that too, right? So what I want you to do now, so basically what we are doing in this optimization point of view, we want to find a minimum cost perfect matching, right? And it turns out that if you can describe this polytope nicely using linear inequalities, because every polyhedron, which includes polytopes, can be written as a set of linear inequalities. So if you can write down this polytope as you can describe it as a set of linear inequalities, which means that your extreme points will be exactly the perfect matchings of your graph. And if you somehow figure out how to optimize over this polytope, then you will be able to find a minimum cost perfect matching efficiently. that is where we are heading, right? So rather than looking for a minimum cost perfect matching, because there are exponentially many perfect matchings, one of the ways to tackle this problem, which is basically what we are going to do when we discuss the primal dual algorithms going further, we are going to look at the polytope. And this polytope is a nice geometric object. So we can use a lot of tools coming from geometry and algebra. And we can try to solve this problem on this polytope. So we can try to find a minimum cost point in this polytope. And that will be a minimum cost perfect matching in our given graph. Does that make sense? So this is all at a very high level. I'm just trying to give you an overview of why we are discussing this.
Yeah. Also, like linear programs, the solution is always at the extreme point, right?
There is always an optimal solution that is an extreme point.
So that's why it makes even more sense.
Exactly. Right. So that's the reason why we are discussing this. Since you're already at 12:50, I just want you to think about a particular point. I'll just give a small DIY problem. Actually, maybe it's not so small. So recall the feasibility IP for perfect matchings. So if you recall the feasibility IP, how did we write it? For each edge, we have a variable. We want the variables to be at least 0. And for every vertex of the graph, we want the sum of the edges incident at this vertex, the x's, to be equal to 1. And I'm looking at the LP relaxation actually, right? So I'm removing the integrality constraint. Okay, and we call these the non-negativity and the degree constraints. So these are non-negativity and these are degree constraints. And what I would like you all to think about is that the perfect matching polytope of any graph is contained in the feasible region of this LP. So let's call this LP star, right? So in particular, if you take any convex combination of perfect matchings, it has to satisfy both of these constraints. In particular, you need to show that any convex combination of the perfect matchings of the graph viewed as vectors has to satisfy the non-negativity and degree constraints. I'm going to call this a DIY problem. It might appear on one of your assignments. Okay. And the next question we'll be thinking about is when are they equal? So turns out sometimes the perfect matching polytope is exactly this feasible region. But in other cases, it is a proper subset. So these are also things you might want to think about and might appear in some form or another on your assignment. Okay. So on Wednesday, we will wrap up module 2 and we will start module 3. But yeah, the lecture is officially over. I'm still here for another 10 minutes or so. If there are any questions or concerns. Okay, so I'm going to stop recording.